Animatronics. The word is a portmanteau that describes the engineering of lifelike things for films or theme parks or museums. And I've worked in the field, and I think I represent a pretty typical seat-of-the-pants engineer who figures stuff out as they go. But there's a more rarefied kind of engineer the field attracts, the kind that seems to have dropped from an alien spaceship and designed stuff that works on the first try. And Mark Satrakian is one of those kinds of engineers. His filmography is as long as your arm, from Howard the Duck to Hellboy to Pacific Rim and everything in between. He is a animatronics super genius. I hope I'm not overselling it. He's invited us into his shop to show us some of his creations and just how he pushes the limits of both mechanics and aesthetics to achieve his incredible creations.
Hi, I'm Mark Satrakian. I'm a robotics and animatronics designer working in Los Angeles. I've spent most of my career working on creature effects projects like Men in Black and the Hellboy series. Today, we're here in my shop, and I'm going to show you one of my robotics projects, Axis. This is Axis. Axis is a robotic art piece that I made back in 2014. The story behind Axis is that in 2012, a colleague of mine named Chet Zar, who is, besides being an incredible creature effects sculptor and artist, is also a fine artist himself. And he was curating a group art show. And he invited me to make something for the show. So in my career as a creature effects guy, I've done a lot of animatronic mechanisms. I've done a lot of tentacles. I've done a lot of mechanical hands, which I really love doing both of those things. I've also done faces and lip sync and eyes and all these sorts of various things. But hands and tentacles are two things that I've really had a lot of fun with in my career. So the first thing that I made for Chet's show in 2012 was a mechanical tentacle, an artistic, abstract tentacle called Cascade. And for the show coming up in 2014, I wasn't really sure what I was going to do. And I was at the 2013 show, and I was trying to decide what to do, and I was kind of doing this, and I thought, oh yeah, I'll make a hand holding a ball. That'll be easy, I'll just do that. So that was the idea, that was the inception for Axis. And the design process was, I wanted to have it holding a globe, and it's a left hand, it's very specific, and it's kind of threatening looking. Almost everything I make is kind of threatening looking, but it handles the globe in this very delicate way. It has these sharp fingertips, but they're touching the globe and moving it in a graceful and smooth way. So I began the design process by doing a sketch. I just kind of did this very loose sketch, and then I started reinterpreting that sketch in CAD, in a computer design program. And the process was that I would work on the CAD, and then I'd print it out, and then I would draw over it by hand, and then try to reinterpret those things. Because when you're in CAD, it can be very difficult to capture a loose, spontaneous design. So I tried to keep that spontaneity. But the other part of it is the function. How was I going to get the fingertips to hold a sphere and rotate it perfectly? So I'll explain to you how it works. This is one of the finger mechanisms for Axis. This is a 3-degree of freedom mechanical limb, basically. And Axis is very much like a walking robot. It's kind of like a spider lying on its back, spinning a ball on its fingers or its legs. But it's a little different from typical hexapod robots. What I've noticed about most hexapod robots is the orientation of the leg is kind of like this. It comes down, here's the floor, and then there's this joint that swings the leg back and forth. But what I needed to do was have the leg balance something on the tip, like this. But if you see, if that axis is lined up like that, then when the finger turns, it doesn't actually go anywhere. So I turned this, and now I have all of this motion, the leg pointing up, touch the ball. So how do I figure out how to get this thing to spin a sphere? Again, I was starting from basically square zero. I had no idea how to do it. So I called upon high school trigonometry. And really what I'm doing is I'm controlling the location of the tip of the leg like this. And I defined a plane that all these axes, these little axes here pass through, and I define the plane that the ball is going to be sitting on. So between this point and this plane, I can draw a triangle that determines how far over it's going when it rolls like this. Then there's another triangle that describes this direction between here and this line. And then finally, between this point and this joint, and between this joint and the tip, there's another triangle. So if I solve all three of those triangles, I can drive this point, we call inverse kinematics. I can drive this point however I want. So I define this point in space and just drag it around. And then every finger has its own set of controls. So in this way, that math, once it was solved, it just totally goes into the background. And I can really start focusing on performance, which is really the important thing to me about how Axis works. This is Axis 2. The way this robot came about is that in 2014, my friends from BattleBots called me up and said, "Hey, Mark, we saw your robot Axis. It's really cool. Can we use it on BattleBots to hold the trophy?" And I don't know if you've seen BattleBots, but the trophy is a giant nut machined out of a billet of aluminum. It weighs about 40 pounds. And I said, no, Axis cannot handle that. It's too heavy. But I can make you one that can do it. And so that's how this robot came to be. There are a few big differences between Axis 2 and Axis. One is the weight capacity, and the other is the way it holds the object. Now, with a ball like this is naturally statically stable, meaning that it just wants to fall into the tips of the fingers. It's like it's resting on a tripod, so it's always stable. But for BattleBots, it was going to have to handle something that was flat on the bottom. And in that case, there's nothing to keep it from sliding around. So I had to address that in a couple of ways. One thing that I did was change the design. Axis is a hand. It has 4 fingers and a thumb. And because of that layout, each finger has a slightly different load capacity than the others. The thumb has a little bit of less mechanical advantage. These fingers are laid out in perfect radial symmetry. So each finger has the exact same mechanical advantage as the one next to it. The fingers themselves are burlier than the Axis fingers. They're shorter, which gives them more leverage. The servos are bigger. Here's the original Axis finger, and you can see the difference. This actually is larger. It's larger, but it's more delicate. This is much sturdier. And then finally, there's a camera in the center of the palm of the hand pointing straight up. And what that does is it allows me to optically stabilize this disc. So this is a plexiglass disc, and normally the trophy would be sitting right on top of this, and there's a black dot right there. And if I put this on Axis and activate the stabilization, the camera sees that dot, and now the robot will respond when this disc moves around. And let's just put some awkward object on here. So now, as I poke at this, the robot will always walk towards the center. It's a walking machine, it's walking in a circle, and it's walking towards the dot. If the dot shifts over this way, the robot will pull it back to center again. And that's Axis 2. Axis is driven by servo motors. And these servos, which look like this, are a complete little motion control package. There is an electric motor in here, there's a microcontroller, there's a feedback device, which measures the rotation of the wheel, and there's also gearing, a gear head that gears down the motor and gives it all of its strength. I think one of the really common misconceptions about robots is that they're super strong. And certainly the big ones really are strong. But pound for pound, a human is way stronger than a robot. And the reason for that is that our technology of putting motors with gear heads into packages like this is just very limited. I use sometimes very small servos, sometimes bigger ones like this. And these are pretty strong, but still, by weight, they're not as strong as a person, which is where hydraulics comes in. So this guy is the skeleton of a hydraulic fighting robot from Robot Combat League. And the hydraulics are a combination of this hydraulic cylinder and this valve. And what happens is high-pressure fluid gets pumped into this thing. It's controlled by this valve, which is equivalent to the microcontroller control in the servo. And then it gets driven into this piston here. And the piston is kind of like the gear reduction. It takes that mechanical force of the flowing fluid and it turns it into the movement of this back and forth. But the motor part isn't in the robot. It's 50 feet away on the end of a hose, and the motor is giant. It's like a giant V8 with this huge reservoir of fluid. So you've got this incredibly big, heavy machine pumping super high pressure hydraulic fluid down a hose, a big hose like this one, into this robot. And then in this area here, thousands of pounds of force can get generated. So when you need something that's incredibly strong, you can use hydraulics. But in general, it's very difficult to get all that power into a single package. Obviously, Boston Dynamics has done a great job with that. But for something like this, it had to be even stronger, which is why it's at the end of a hose. And that's hydraulics. The control system I wrote for Axis is a gate generator, a gate being a walking gate. And it can work with any number of legs. Axis has 5 fingers, so it's like a pentapod. It's a 5-legged machine that walks. It also works for bipeds. The robot behind me is Hades. Hades was the prototype robot for a show I worked on called Robot Combat League. And there was a similar gate generator developed for this robot. It uses waves as well. And the controls are direction, in other words, the direction the step is going to go, speed, how fast it's going, and also amplitude, which is the amplitude of the wave, which basically controls how big of a step it will take. The controls were very simple, but the people who were running them figured out all kinds of clever ways of manipulating them. One of the things that surprised me was one of the guys had this technique where he would turn the speed down to 0 and then jam on the amplitude, and the robot would suddenly snap into a fighting pose, which was really cool and really unexpected. I didn't imagine that was going to be possible. But that's one of the great things about doing projects like this, is the surprises. So while I've got Axis 2 set up here, I want to try a couple things. I think of Axis as like a robot. It runs software, it's a machine, it has these motions that it does, and it doesn't really require any human interaction. To get down to really how this motion is generated, I would describe it as like a synthesizer, like a music synthesizer, except instead of synthesizing sound, the oscillators are providing motions. So the motion of each leg is a pair of waveforms. There's one wave, which is the arm going back and forth, rising and falling. And then the other waveform is the foot stepping off the surface of the ball and coming back down again. So it's flat, and then it arches. And these two waves are in phase with each other. And then each of the 5 legs has an identical pair of waveforms, and they're all in phase with each other. And it creates this cyclic motion. And you can see how at any given time there's at least 3 legs in contact with the ball. 2 of them are lifting off. So this is algorithmic motion. But there's another way of controlling Axis, because, like any of the robots that I make, this thing can also be used as a puppet. So I've got some basic controls here that allow me to move the ball around with my puppet controller that I use on movies. So there's 2 things going on here. One is I've got the joystick control of the ball. And you can see the movement is pretty smooth. One of the reasons why it's smooth is because I'm running the output of the joystick through a filter. If I turn the filters down to 0, you can see that it's capable of these very jittery, almost uncontrollable motions. And what that's doing is this filter, like an audio filter, is filtering out the fastest motions. So the highest frequency motions are being suppressed, and only the languid, fluid motions come through when I turn the filter up. So if I turn this back up again, and now that it's starting to get a little squishy again. And when I'm working on a movie set, controlling a robot or a creature, these filters become part of the performance toolkit that I use to get a smooth performance or a very agitated performance, just whatever I need. I have control over that, and I have choices as to what I'm making. But the cool thing about this is that I can run this input, and I can run the algorithmic input at the same time. So let's just turn this up a little bit. So now I've got that cyclical algorithmic motion and a live input performance going simultaneously. And this is really like the full kit of tools that I use when I'm running a creature or a robot in an animatronic situation, puppeteering on a movie. This is really fun. Thank you for joining me here. I hope you enjoyed learning a little bit more about Axis and Axis 2 and learning about how these robots work. The next time you see something animatronic on screen, you'll have a little better idea of what's going on behind the scenes. Thanks again.